Okay, so I am just going to go over the basic stuff. So let me start with what a spiral similarity is. So you can probably think of it like a function, basically, that maps like some point of the plane A to another point of the plane B. And this function is going to have like a very specific structure, which is that. So basically, I think all of you know about homotheity. A homotheity is basically a scaling or a similarity. So in that, you just have like a center of homotheity, you have some line or some conic, whatever, and you scale it so that these are like, yeah, it's just scaling, right? So this, if this is k, then this is lambda times k. So this is what homotheity is. And for spiral similarity, it is a function that basically combines two things, which is homotheity plus rotation. So basically the point is, if you have some triangle here, and okay, this looks very equilateral. I'll just change that. Yeah, let's just say that you have a triangle ABC and you are sort of dilating it. So yeah, this is some triangle A prime, B prime, C prime similar to ABC. These are similar. And if you rotate this like a little bit, so it's going to look something like this, I guess. Yeah. Let's say A double prime, B double prime, C double prime. Then this is a homotheity. This is a rotation. And like this, or this, like the opposite direction, this is a spisim. So this is basically what a spiral similarity is. And okay, so one of the first things that you want to talk about while doing spiral similarity is that how do I determine what the center of the spiral similarity is, and how do I determine if the spiral similarity is like unique or something like that. So the point that I wanted to make is that it is like a dilation composed with a rotation. So now I want to like claim that a spiral similarity, like basically it is going to be unique in a sense. So if you have two segments, like I will just draw them like this. So AB and some CD. Then there is going to be some center O here that sends the segment AB to CB. And this is like the notation for spiral similarity. And if you are not comfortable with this, there is another notation that I most commonly use, which is you have to send A to C and B to D. By the way, it's being recorded, right? I am not sure. Okay, yeah, it is. Sure. So, like you are going to have some center O that is going to send A to C and B to D. And what this means is that triangle OAB is going to be similar to triangle OCD. And another interesting fact about spiral similarities, which we will prove later, is that if you have this, like OAB and OCD are similar, then you are also going to have that O, okay, so O sends this, right? So O will also send A to B and C to D. So you basically take it to be like this. So if it sends A to C and B to D, then it will also send like A to B and C to D. That is like the condition of the spice sim. So the first few questions that arises probably are, if there are two segments AB and CD, like is there a unique center of spiral similarity? That is the first quick question. So I'll just write them down. Unique. And the second question is that, like, even if we get like a center of spiral similarity by computation, we can use complex numbers or coordinates or anything. So even if we get a center, like how to determine it geometrically? geometrically determine. Yeah, these are the two main questions. So, like, first of all, like everything I said till this, like, is everything clear to everybody? Like, any questions about what spiral similarity is, or what I'm trying to say, what I'm trying to claim and prove? And it'll be better. Okay, what do you mean by
Hey,
geometry? Yeah.
okay, you answer that.
Okay, sure. So by geometrically, I mean that if you have 2 points A and B, like A and B, and other 2 points C and D, say, then the point is that there will always exist a spiral similarity that is going to send like the segment AB to the segment CD. Okay, and this we will prove, and that center of spiral similarity is going to be unique. So the point is that by geometrically, I mean that if you take the complex numbers for these, say A and B, C and D, then after like a bit of computation, you're going to get the expression for this particular O. But let's just say you have a ruler and a compass. Like, how could you sort of construct this O? So my aim is going to be construct with ruler and compass. That's basically what geometrically means here. And Arham, what? Okay, does this answer your question? Okay, yeah.
Like,
Yeah.
if there is a center which does this, like, why will it still be similar? I didn't get that.
Oh, why will what
Like,
the center?
if you rotate around OA, if you rotate around O and send A to D, why will OAB be similar to ODC?
Okay, sure. Good question, I guess. So basically, this is not just a rotation. So notice that I first said that this is a dilation and a rotation. I don't care about the order, but it has to have a dilation and a rotation. So if you sort of rotate it,
Yeah.
like to come here, like rotate, okay, let's just say that after complex bashing you got the coordinates of O, and then you want to rotate OB to align with OC. So now OB is OC, like B is somewhere here, right? B will fall somewhere here. Let's call it B prime. So like since these two triangles, like center of spiral similarity means what? The triangles remain the same, right? So A is also going to align here because these two triangles are just uh,
Oh, okay. I see. I got
that.
it. Thanks.
Yeah. Okay. So these are also going to be parallel because similar, of course. So yeah, that is the point. So this
Uh,
angle is theta. Yeah.
yeah,
Anybody?
to geometrically construct O, couldn't we like just set an arbitrary point as like origin in the complex plane, do whatever the transformation for the spiral sim actually gives us, and then just plot it there?
Okay. So the point is that you can't plot it in a sense, right? You won't have a graph paper and all.
No,
So
but
by
like you can obviously draw parallel lines. So if you're shifting B to O, I mean
yeah.
0, then you can shift A to A minus B quite clearly. Compass for length, and angles, you can replicate angles. So
Sure.
I mean technically you could just find O just doing whatever operations is there in the nested complex formula.
Okay, so I get what you're trying to say, but there is one drawback to that. So let's just say you have some AB and you have some CD here, and you are saying that you want to take any arbitrary point to be the origin. Like let's say that you're taking P to be the origin, and you are saying that you will like translate to align one of these points to be the origin, right? Is that what you're saying?
No, so for like the point O which sends AB to CD, right?
Yeah.
We have a determined geometric, I mean complex formula for
Yeah,
that,
yeah, yeah. You have a complex number, let's say C.
right? So what we can do is basically just taking any of the points, say A, right?
Yeah.
Just do whatever transformations required to
Okay.
convert point A into that point C,
Okay, sure.
and then you get point C.
Okay,
Example,
that
hold up. I'm forgetting the exact formula for spiral sim.
okay, like cool. I get what you're trying to say, but let's okay, for that let's compute what exactly O is going to be in terms of A, B, and C and D, and then I'll answer your question.
Fine.
Does that make sense?
I think I have a way to construct O.
Okay, go ahead.
So basically, you could draw a perpendicular to AB from B,
Okay.
and then you do the same to CD from D, I guess, and then you mark the point where they intersect. You do the same for C and A as well. And then you just draw the circumcircles of so if you like consider the like meeting point of A, like the perpendicular from A and C as, I don't know, X maybe, and then B and D as Y, then the circumcircle of ACX and BDY, wherever they intersect, I think that would be the center of spiral similarity.
ACX and BDY. Okay. Forgive my drawing. This is terrible. Wow, it didn't even render as a circle. One sec, let me check. Yeah, this is probably it. Okay. You are saying that this is the center of SpySim. And why? What is the proof?
Like I think it's because like I didn't like exactly like formally prove it, but I
Okay.
like if you take BD, like the line BD, and then you just think of it like as similar triangles, and you're basically like shifting like an angle like BO such that angle ABO equals angle CDO, then angle BOD always remains a constant. So like that means it must lie on that circle. And then the same for uh like uh like angle AOC. So like angle BOD and angle AOC always must remain a constant. So they have to lie on that circle. So
Okay. So one drawback here. You are saying that BOD and AOC must remain like constant. Is that right?
yeah, constant for that, yeah.
Okay. But if you like, let's just forget that this is our O, okay? So let's just say that this is our O, like center of SpySim. And this center is going to send this segment, okay, wait, this segment AB to the segment CD. Then it is sort of like a rotation first and then a dilation, right?
Yeah.
Okay, so if you rotate this like OAB triangle, it is going to lie somewhere here, such that these are parallel, right?
Yeah.
A prime, B prime, the same thing I was telling Arham then. Yeah. So this is the center of spiral similarity that sends AB to A prime B prime. But
Yeah.
if you rotate this triangle a little more, like if you make it to be this, and then you say that you dilate it like this. Okay. A1, B1. Then also, O is the center of spiral similarity that sends AB to A1, B1, right?
Yeah.
But BOD and BOB1 are not equal, so it does not remain constant.
Sorry, BOD and which angle?
BOB1. Like those are the corresponding angles, right? You are taking the angle between BO and where BO maps to. But here BO maps to B1O, right? But B1O B and DOB are not equal. So the angles do not remain constant if you are taking a spiral similarity from this segment to another segment.
Like sorry, I didn't mean it like that. Like basically if you like just take angle like basically you want triangles ABO and OCD to be like similar. So
Yes.
so then angle ABO and angle CDO must be the same.
Right,
So
right.
if you
Okay.
construct BD, so once you construct BD, what happens is you have angle OBD plus angle ODB to
Yeah.
always be equal to, I think, angle ABD plus angle CDB minus, I think, one of those angles. So, like, it always remains constant in that sense, like, with
Right.
relative to, like, those two segments.
Right, okay. So I am not exactly sure if this construction is right. I will have to check it in a little while. So I'll just go over the complex number first and then I'll leave you with another construction and you can sort of check on your own if both of these constructions lead to the same point. Does that make sense?
Yeah, sure.
Okay. So now I want to find out the complex number. Yeah. For center of spiral sim. So how can I say that the complex number is going to, like the center of spiral similarity is going to be unique? So let us take the same diagram again, like some AB and some O, some CD, I guess. Yeah. Okay. So these two triangles are similar. So let us like take the complex numbers of these to be A, B, C, D. Alright. So basically the angle AOB is equal to the angle COD, right? And how do we determine angles in terms of complex numbers? Like we take the slope of the lines and then we divide them, right? Does everybody know this?
Yeah.
Okay, cool. So angle AOB equal to angle COD, we can interpret this as, this is going to be interpreted as B minus O by A minus O is equal to D minus O by C minus O, right? So let's expand. BC minus BO minus CO squared is AD minus AO minus DO plus O squared. So you get that O into A plus D minus B minus C is AD minus BC. So O is equal to AD minus BC by A plus D minus B minus C, which is unique, right? So you get a particular formula for the complex number. Does this make sense? It's just calculation. Is this clear to everybody?
Yeah.
Yeah, okay. So, therefore, this is going to be uniquely determined by A, B, C, and D, right? Yeah. Also, like, there is one case when the center of spiral similarity does not exist. When
When they're
does...
parallel, right?
Sorry?
When the lines are parallel.
Yeah, exactly. Yeah. So the answer to this is like ABCD parallelogram, because ABCD parallelogram implies A plus C is equal to what? One sec. ABCD. I guess not. B plus C. Oh yeah, ABCD parallelogram just means A plus D equal to B plus C, right? Okay, that was just a guess. Yeah. So this would mean that O is, denominator of O is 0. So it's not defined then. So this is the complex formula for our center of spiral similarity. It is not important to remember. You can just find it out at any point if you need it. Yeah, okay. Cool. Let us now move on to the geometrical representation of the center of spiral similarity. So let's just say you have two segments AB and CD, and you want to find the center of spiral similarity that sends AB to CD. So I'll draw the same diagram again. AB and okay, yeah, sure. I'll just draw it like this. Yeah, this is the diagram. So I am claiming that If you want to send AB to CD, so you take the intersection of the other one. So let me write what I want. I want AB to go to CD. So I will take the intersection of segments AC and BD. Right? And then I will mark this to be some P. Is this fine? Okay, and then I'll take two circumcircles. One of PAB and the, okay, this is a bad diagram, turning out to be a bad one. Sorry about this. Yeah, okay. Better, I guess. And I will also take the circumcircle of PCD, if this is a circle. Okay, yeah, it is. One sec. Wow. Okay, this is weird. I'll just make it an ellipse. Don't mind, just to fit in this. So anyway, if you take the intersection of these two circles and call this point X, I guess. Can you prove now that? So I'm claiming triangle XAB is similar to triangle XCD. Can you try to prove this real quick? Just verify. Anyone? Any progress?
Yes.
Yeah, go ahead.
Like we just take it's enough to prove angle XAB is equal to angle XCD, but angle XAB is equal to angle XPB, which is equal to angle XPD, which is equal to angle XCD.
Perfect, yeah. So I'll just repeat what Bhairav said. So it is enough to prove that angle XAB is equal to angle XCD in here, right? So angle XAB is equal to 180 minus, sure, wait, what? Oh yeah, of course. So XAB is equal to angle XPC, right? Because exterior angle of cyclic quad. Wait, what?
Wait, no, that's not right.
Okay, I'm majorly skill is showing here. One sec. What? Okay, I have a glitch. Sure. Okay, I want to prove that XAB is XCD, XCD is this. Yeah, this is just true, right? This chase. Yeah, of course. So XAB is equal to XPD by exterior angle of cyclic quads, and XPD is equal to XCD. So I'll just write it down. XAB is XPD is XCD. So done. So yeah, so this is the center of SPICEM. So
I
if,
have a question.
yeah, go ahead.
What do we do if P is one of the points A, B, C, or D?
P is one of the points A, B, C, or D.
Example, C lies on AB. Then we get P is equal to B.
Something like this. A, B, C, D. You're talking
Yeah,
about
something like
this.
that. The circles are undefined.
Okay.
I was thinking we could take a limit of a point approaching C to define the circle, and we should get a
Yeah, you should get the limit of the intersection of the circles as well, and that should be the center of SPICEM.
would that work?
I think so, yeah.
Right. Thank you.
Okay, let me. Um, just a sec. I'll just think about it. What happens for a degenerate case? Okay, I think that should work actually. Yeah, never mind. Okay, yeah. Anyway, so this is the center that takes AB to CD. So if you don't want to write it like AB to CD, you can just write it like A goes to C and B goes to D. But remember that in the beginning, I said that if there is a spiral similarity that sends A to B and C to D, then it will also send, okay, what? Oh no, A to C and B to D. So at the very beginning, I said that if it sends A to C and B to D, then it will send A to B and C to D. So can you try to prove that X also sends this? So, okay, I'll just prove it for you because it's very trivial. So it is enough to show now that...
Wait, if it's a function, how is it sending A to 2 points?
Like, it is not a function. Like, I could try to think about it as a function. Like, a spiral similarity is not a function. It is like a transformation, an affine transformation.
Okay.
But like, for people who have never heard about it previously, it is easier to think about it like a function because, you know, a point gets sent to another point. How else do you say
Wait,
that? That's
so
very
you're saying the spiral center of AC and BD is also X.
Yes, exactly.
Oh, okay, that makes sense.
So it is enough to show that triangle XAC is similar to triangle XBD, right? And this is true because angle XAC is equal to okay, what do I want to show that it is equal to? XBD, right? Okay. Yeah, of course it is equal to XBD, right? Just inscribed angle. Yeah. And similarly for the other angles. So this is true. Okay, I will stop sharing for a second. One sec. I'm running out of space on my Miro. Yes, this should be better. Okay, do you see the screen? Okay, cool. So, therefore, if X is the center of spiral similarity that sends A to B and C to D, then it will also send A to C and B to D. And the reason that I'm saying this multiple times is that try to keep this in mind because this is going to be very important while you're solving problems. So yeah, this is the first thing that I wanted to say. Now there is a very important config that probably goes hand in hand with spiral similarities. So that is the Miquel point config. So I will just not make a fool of myself and make a good diagram of Miquel points in GeoGebra. So I'll share my screen. Okay. Yes. Okay, so here is GeoGebra. Okay, so for a Miquel point, we are basically going to have 4 lines, like 4 points, and of course 4 lines. Doesn't matter. So say something like this. Okay, this zoom is freaking me out. Okay, and 2 other lines, AC and BD. And we are going to take the intersections, of course. And we are also going to take the intersections of these. So this is what is called a complete quadrilateral. So in this diagram, ABCD is a complete quadrilateral. And the way that we define a complete quadrilateral is that if we have a quadrilateral whose extended sides and diagonals are already intersected, then that's a complete quadrilateral. So a special case of this is obviously going to be when ABCD is cyclic. So we'll come to that later. But for this general thing, like a couple of stuff is true. So I will go over the things. Anyway, so there are a lot of circles in this configuration that are concurrent. So I will just show you the circles first and then we'll move on to proving the things. So okay, I'll just say that systematically. So ABCD, okay, it's ABDC but doesn't really matter. So the point is that EAB and ECD, let's take those two circles first. They intersect at some point P, right? Like whatever, any point. Then I'm claiming that the circles, okay, what? GGB skill is showing now. One sec. Yeah. Then I'm claiming that BDF and ACF are also going to pass through this point. So I'll just draw it for you to see. So the point is that this is basically Miquel's theorem. This is Miquel's theorem, and this happens in general for any quadrilateral ABCD. So I will go back to Miro and try to prove this. Okay, yes. So again, I will just copy paste the diagram with a little less circles, I guess. Yes. Like complete quad diagrams are such a pain to draw without your usual compass and stuff. Yes. So the first thing is that I'll just repeat what I said there. So if ABCD, like ABDC here, is a quadrilateral and you take the extended side intersections and the intersection of the diagonals, then that is a complete quadrilateral. And there are a couple of circles in a complete quadrilateral that pass through one fixed point. So if this is your quadrilateral and these are the diagonal intersections, then an easy way to remember it is that EAB here, ECD, then BDF here, somewhere here, and ACF. Can you visualize these things? Like these are going to be concurrent. Did I was I clear with this? Like, did I make sense? Anybody?
Yes.
Okay, perfect. So I could try to prove this, but like it is a very easy proof to be honest. So what do I want to show? I want to show that BDFH is cyclic. So the thing that I can do to prove that is angle. Okay, just try to come up with a quick angle chase. Like this is very trivial. I'll wait. Something in the chat. Okay, renamed. I don't care. Like GGB gave me the name and I just stuck with it. Like name it whatever you want. Doesn't really matter. Okay, so sure. I will just not go over this angle chasing proof because it's something you can do at home as well. So there are two proofs. Like one is an angle chase, which is pretty easy to come up with. The second proof is PySim. So I'll do the PySim proof now. So can anybody give me any intuition on what you're thinking? Like it's not good if I just say the proof and you agree with me. Any intuition? Okay, people are unusually quiet here. Okay, go ahead. Yeah.
Could we do spiral like similarity, like using the intersection of AC and BD? Like
Perfect.
that would be like on AB and CD basically.
Precisely. Yeah. Great job. So H is the spiral similarity ka center. H is center of spisim that sends what? A to C and B to D, right? Because we are taking AC intersection BD and then we are drawing the circumcircles. This makes sense? Okay, so it also and like speak up, please, because it's hard to keep going on a monologue. So it also sends A to B and C to D. So this means that if it sends A to B and C to D, then if you take AB intersection CD to be F, then H is also going to lie on FBD and FAC, right? Hence done. So this is like a very nice thing, right? We have such a random quadrilateral, like any quadrilateral, and we have four circles that pass through this single point. So this is indeed a great theorem.
Wait, why is H in center of the first specimen?
Because you are taking AC intersection BD
Yeah.
and it is this point E, and you are taking the intersection of circles EAB and ECD. That is how I defined like it geometrically, right? If you want A to go to C and B to go to D, then it is the
Yeah.
intersection of AC and BD, and you take the circumcircles ABP and CPD, and
Oh,
you
I
take the
think I got confused because the quadrilateral name is different.
Oh, okay. Okay, I'll just name
Yeah,
it.
I got it now.
Okay, sure. All right. So this is the main Miquel theorem, I guess. So there are a couple of properties about Miquel point of cyclic quadrilaterals and also non-cyclic quadrilaterals. So I will sort of state them systematically, but I am not sure how much time I will have to prove each one of them because we also have to do a couple of problems. So I kind of wanted to keep the last half an hour for problems, but I don't think like I'll be able to do like many problems because also is anybody already familiar with this and needs buffer problems? Just speak up because I have a couple of problems I can share. Oh, okay. You should have said earlier. Let me just share a buffer problem. Okay. Try this one, I guess. USA TSTST 2017 P2. I'll write that down. TSTST 17 P2. Buffer. Okay, so I will state the Miquel properties systematically, and I would advise you to try to prove these things because it is going to be very useful in problem solving. So if
2017, right?
yes, 2017 P2.
It seems to be a combi problem.
Lama, I'll paste the problem. Wait, that should not be the case, but wait a sec, my internet is cooked. Okay, is it combi? My bad then. Yes, here you go. Okay, I'll not like waste more time. So yeah, so if ABCD is like a quad, and I will have a common diagram for all of these, and I don't want to make the names confusing. And also, I'm not checking chat, so if you have anything to say, just speak up. So if ABCD is a quadrilateral, and this is say E, this is F, and the inside one is G, and this is O. So this is going to be my reference diagram for everything. So then circle BCE, ADE, FAB, and FCD concur at M. So here is M and it is the Miquel point. The first thing, yeah. The second thing is that if you have a cyclic quadrilateral ABCD, if ABCD is cyclic, then M is the inverse of G with respect to circumcircle of ABCD. So in order to prove this, you can do a phantom point argument. So assume that M prime is the inverse of G, and then you can just chase a little bit of angles, like inversion angles. I think inversion has been done before on OMC. So yeah, you can just chase some angles and you'll be done with this proof. So yeah, that is the first. Okay, that is one of the things I wanted to say. Okay, why is the chat flooded? Oh, okay, thank you. I did it. Oh yeah, it is TSTST. Yes. Cool. Then another property is that if you take the centers of all of these circles, then they are also going to be concyclic. So that's a separate circle which is not really famous, but it's just something to keep in mind. So centers of BCE, ADE, blah, are cyclic. This is also something you can keep in mind. Just going over some properties, and another property is altitudes from M to the sides are collinear. So if you want rigorous proofs of these things, then you can probably refer to EGMO. EGMO has nice walkthroughs. So yeah, this is probably everything you need to know about Miquel points. And now I'll just go over how Miquel points are related to spiral similarity now. So, okay, let's just take this diagram and let's rename the points. Okay, this is M and this is F. Yeah. So these are also cyclic, right? M, C, B, and E. And M, D, E, and F. This is what I said a little bit back. Sorry for the messy diagram. Okay, so, okay, some question. And please interrupt me and speak because hard to see. For the second property, what is the inversion with respect to? Yeah, it's with respect to ABCD. Okay. Cool. So, since there are a lot of circles and both of the intersections of each of the circles are known, can you spot some spiral similarity in here? Can you spot some segments that go to each other? Just inviting some ideas in. Can you see something going on? I'll give you a few minutes to look at this. Try to think about various... Okay, so the way to think about this is you take two segments, you take their intersection, and you like, let's say AB and CD, you take their intersection to be P, and then you take the intersection of circles PAC and PBD, and the second intersection of those circles, and that is going to be the center of spiral similarity, which is going to send AB to CD. So can you try to think about anything like that? Just, yeah, unmute and speak if you can find something.
So what are we supposed to search for?
Any spiral similarity pairs that you can find here. Yeah.
I think AF and CE.
AF, okay, let me go back to the diagram. AF and CE, okay, that is one, definitely. So I'll just keep a note. AF goes to CE. And what is the center of spiral sim?
M.
Yes, perfect. Also, like you said AF to C, which is perfectly fine. So this means that A goes to C, F goes to E, right? So another pair that you can get from here?
What were the points again? A. Yeah. Oh, okay. Yeah. FC and AE.
Perfect, yes. So in the particular order that you would want to say, so here A goes to F, C goes to E. So you can also, oh wait, okay. A goes to F and C goes to E. So AC goes to FE. Yeah. And Bhairav, what did you want to say?
Wait, how do we get AC goes to FE?
Is that wrong? I don't know.
I think so. Because
AC goes to FE. You know what? That kind of seems wrong. And also, like, just to clarify, this is in the case of a cyclic quadrilateral ABCD. Like,
Oh, wait, wouldn't it be FC to AE?
okay, I think I messed up the order. Oh wait, this is not CE, no, this is EC. Damn. Okay. Then I think it should work out. AF goes.
I don't think AF should go to EC.
It should, because you are taking AE intersection CF, which is B.
Wait, right, yes. Sorry.
So A goes to E, F goes to C, and that means like segment AE is also going to go to like FC. So these are two pairs. Does this make sense to everybody? And also, Shaurya, we are not doing a problem, like it is Miquel config, like you said, yeah. Okay, I'll just go over it because we don't have much time. So another thing you can note is that AD intersection BC is F, and you're taking the circumcircles of ABF and ACD. So basically, M also sends A to D and B to C. So, okay, I'll just write it like this, So A to E, F to C is one, A to F, E to C is another. Then A to B, D to C is another. This would give rise to this. And there is one more pair that you can find, which is like B goes to A, C goes to D. And that gives rise to B goes to C, A goes to D. Yes, so these are the 6 spiral similarity pairs that you get. So this was essentially to demonstrate that SPICEM and Miquel just sort of go hand in hand. And if you have like any Miquel config, you have a lot of similar triangles to angle chase on. And of course, you also have a lot of circles to angle chase on. So yeah, this is probably it. So I'll just start with a couple of problems because yeah, we haven't done any problems till now. So I'll just do a problem that is very instructive in terms of like learning Miquel and Spicem. I'll just paste it here. Give me one sec. Okay. Yes, this is it. And the sources. Okay, I'll give you a couple of minutes to read and make sense of it. Also, if you have any progress at any point, just unmute and speak up. Oh, I kind of could paste the diagram. Do you want me to paste the diagram already, or do you want to take some more time to not look at the diagram and write on your own? Okay, I'll not paste it, but do speak up, I guess. Any thoughts? Anybody? Okay, never mind. I'll paste the diagram once. And this is drawn in GGB just to conceal my noobness in drawing digital diagrams. Like, I would advise you to not do it in GGB. Oh my god, some people were waiting for the nice diagram that I mentioned I would paste. Like, I think I should get you started or something. So, what do you exactly want to prove? Okay, I'll just go over the problem before saying what you want to prove. So, you are given D and E on segments AB and AC such that AC is okay. Solved? Okay, go ahead, I guess. Can you unmute and speak, because I think that'll save a lot of time instead of looking at chat. Okay, you want me to do it? Okay, sure. I'll just probably give some motivation on how to think about this, I guess, and not solve it directly. Okay, so what is given? D and E are given on AV and AC. So how are you constructing D and E? So you're taking the circle centered at C and with radius CA, and you're taking the intersection of that circle with AB segment. Similarly for E, you construct E like that, right? Okay, so that is how D and E goes. Now, what are you said? You take the circumcircle of ADE and you take P to be the reflection of A across BC. So, also notice that I drew these circles which were a little bit unnecessary, like circle ADC, like AD, just the circle through A and D centered at C, and the circle through A and E centered at B. And those, let's say that those intersect at P. Then I'm claiming that this P is the P that we want, that is a reflection across A. Can everybody see why?
Yes.
Okay.
Not really.
Sorry, you want me to say it?
Yeah, can you wait? I'll just think about it for a moment.
Okay, yeah, that is great. Just think about it for a minute, and then if you don't get it, I'll say. Okay, somebody said that it is true, like P is the reflection across of A across BC. Like how? If you want to share.
So basically the radius, oh, like, yeah, so is it fine if I should say it, or?
Yeah. Go ahead.
So basically the radius through C, like you could extend it to CB, and then you have A like the reflection of A across CB to be like the point P. So you're basically just having like
No.
a perpendicular.
Why is the reflection of A across BC the point P? That's what
Um,
I'm asking actually.
Yeah, it's like a perpendicular bisector. So then you have like whatever point where AP intersects like CB, if you call it X, I don't know. Like if you call it X, then both of those triangles AXC and CXP are both congruent. So since they're congruent, AC equals CP. So it like, Yeah, it has to be centered at C.
Yep.
With the
Great.
circle.
Yeah. Okay. So first claim is that.
Oh wait, is it also because
Yeah.
the line joining the centers is the perpendicular bisector of the common chord?
Yes. That is also another way to say it. Like, yeah. Like what the previous person, like, I think what Ashwath said was just the proof of that, but yeah, it's just
Oh,
what he said.
okay.
Yeah. So the first claim is P is equal to circle centered at C through A. What? Okay. Through A cap circle centered at B through A. Yes. And this claim is done, right? So now what are we given? PD and PE meet this circumcircle of ADE at x and y. And I want to prove that BX and CY intersect in this small circle as well, this point. So x and y are basically like nothing. Just you take what? Yeah, you take PD and PE and let them meet the circle for the second time. So those are x and y. And now you want to show that BX and CY intersect on omega. So, like, can you see something that you have to prove, like some enough to show thing in terms of SPICEM? Like SPICEM has a very interesting thing, like if you want to send AB to some CD, then you take the intersection, the intersection, and you take the second intersection of the circles, right? Whatever, yeah. So this is what SPICEM says.
Just
So
a
now you,
question.
yeah,
Sorry, I just have like a guess.
go
Not
ahead.
proof yet. Is the A the pi center of of CY and BX? Is that's what you have to show?
A is this,
A is the spiral center of CY and
yes,
BX.
exactly. Or you can say it like XY to BC, like it sends XY to BC. That is enough to show, right? Great job. XY to BC. And why is it enough to show? I'll just say that real quick. So if A sends XY to VC, then XB cap YC is going to lie on the circumcircle of AXY and ABC, right? Does that make sense? And I want it to lie on the circumcircle of AXY. I'm just looking at it in a reverse direction. So I kind of want what? Okay, no, did I say that right? Okay, yeah, I did say that right. So I want XY to go to BC. So like I basically want XB cap YC to lie on this circle. So that is equivalent to XY going to VC by spiral similarity. So, okay, you want me to repeat. So I meant that it is enough to show that A is the center of spiral similarity that sends XY to BC. And why is this? Because if it sends XY to BC, like XY to BC means what? X to B, Y to C, right? So that means the intersection of YC and XB, that is going to lie on this circle, and that is what we want to prove. Yeah, got it. Okay. So just, I guess I would say angle chase and tell me the chase. And also in the angle chase, you are going to have to use that P is the reflection of A cross.
I think we might not need angle chase directly here because it's enough to prove that AD is similar to ABC because
What?
ADE or AXY?
I
AXY.
mean no because AXY X is the reflection of E and Y is reflection of D and AP.
Y is the reflection of E. Ah, I see what you're trying to say. Yeah, that is also true.
So
Yes.
we just need to prove first that claim and then we need to prove that since that will become equivalent to BCD cyclic.
Uh-huh. Yes. Okay, so that is also like an easier way to prove that. But I'll just like finish it up in this way because I'm halfway through. So what Bhairav said is that like D and Y are reflections across P like AP. Okay, is that okay? Yeah, that is true. What am I saying? Yeah, and X and E are also reflections across AP, and so you can use that to finish, like because then it is enough to show that ADE is similar to ABC. Wait, what? No, ADE is not similar to ABC, no? Or you want AED to be similar to ABC? If ADE were similar to ABC, then DE would be parallel to BC, right?
Not necessarily, I mean negatively similar, which is
Okay.
equivalent to D antiparallel.
Oh yeah, AXY similar to AD, similar to ABC, yeah. So BCED cyclic is also suffices. So can you prove BCED cyclic, which is probably an easy thing to prove?
Wait, why is AXY similar to AED?
Because X is the reflection of E across AP and Y is the reflection of D across AP. So just reflect it across AP, right? So
Just one
AXY
question.
is
How do we know it's that though? I said so, but
Yeah, I
couldn't.
don't see that either.
okay. Is that true, first of all? I don't know if this works because this was not my solution. Let me see.
This should probably be true.
Yes, because BCED is cyclic.
Okay, wait, if we know that BC is cyclic, then it's just equivalent to proving that this thing.
Yeah, AXY similar to AED. It's equivalent to proving that, yeah.
Which is
PBDEC.
equivalent to proving that
PB
EP has angle bisector AP.
center of AED. XDYE is an isosceles trapezium, I agree, with perpendicular bisector AP.
How
So,
is
yeah.
XDY isosceles strip?
Sorry.
How is it an isosceles trapezium?
Oh, because you can like try to. Okay, just take a minute and try to prove that X and E are reflections. It's just angle chase.
Okay, sure.
What's P statement? Also, is this real Adish or is this like somebody else? Oh, hi Adish. Welcome to Spice Sim. Okay, the problem statement is this.
Hello.
Hello.
I, I have decided that it's like I can't really get out of bed, so joining the OMC class is the best use of my time.
Okay, that makes sense. How's college?
Good, good. That's good.
Okay. Yeah, so were you able to prove isosceles trapezium? Reflections, basically. Okay, damn. I'll just go with the solution that I had because people are basically dead. I don't know why, but they are. So, yeah. So I'm going to make a couple of okay, just one claim suffices here, I guess. Claim. So, can you notice that BPDE, DE, right? And BPCE cyclic. So basically, BPDEC cyclic. Like, I don't want to involve the fact that. Oh, okay, wait. Okay, XY is C, no? Actually, what Barrow said works. It's just probably the same. Yeah, okay, that also works. So this is basically what Rijul sir said in chat. So BPDEC and the center of this all are cyclic. I don't want the center right now. It's like not required maybe, but at least BPDE are cyclic. And BPDEC. Yes. Oh, okay. A center and P are collinear. So center helps. Oh. I mean, yes, okay, sure. Yeah, I see that.
Why do we need to prove B, D, E, and C are concyclic? Like Bhairav said earlier, couldn't we like just go ahead and prove uh, triangles ADE and ABC are? I mean,
Yeah,
AC
sure. Like,
similar.
but the point is that this kind of finishes, no? Why would you need that? So, okay, I'll just finish it to end like the confusion here. So, what do I want to show? I want to show that it sends xy to BC, right? Xy to BC. So, it is enough to prove that triangle AXY is similar to triangle ABC, right? Do you agree?
Yeah, yeah.
So, like angle AXY, uh, we
Like I think triangles ABE and ACD are similar. So then that means AD is to AE equals AC is to AB, and angle DAE is a common angle. So like, don't we directly have that triangles DAE and
okay.
CAB are like similar?
This is right, I guess. Is it? Okay, this just finishes, right? This is the chase. Like, just look at it once and you'll get it.
Wait, what is the first step? How did that work?
AXY and PEC. Like,
Yeah.
exterior angle of cyclic quad, AXY and YEC. I just wrote YEC as PEC.
Oh, okay, right.
Yeah, so like you get that AXY is equal to angle B, and similarly angle AYX. Okay, this was copium. What did I take? Sure, yeah. Do you guys understand this?
Yeah.
Wait, what is going on chat? Uh, will detect what? Sure, never mind. So, yeah, this is the solution to this problem. Did this make sense? Everybody, I want a lot of yeses to move on.
Yes.
Yeah.
Great. 2 is not a
Yes.
lot out of 11, but okay, 3. Sure. Never mind. So, this is the first problem that we did. Another exercise that you could try to do using SpySim, that could be a bit instructive, and I don't want to give some people deja vu, but you can do this as homework in 2026 P3. This is also SpySim. I know, right? Okay, I didn't get it in contest either, so welcome to the team. Anyway, it's just an instructive problem, to be honest. Okay. I didn't want to give you trauma, like you said. And also, like, is it okay with everybody if I run like 10 minutes over time or something? I just want to do one more problem. Afterwards. Ooh.
Basically, he just came up with the spasm claims. I accepted them as the truth and then did the rest.
Lamau, okay. So the next problem that we're gonna do is not Inmo. To probably many of your relief. Yeah. I'll paste it. It's a Russia problem and it's like really nice. Okay, what is going on? My laptop is skillish. Yes, got it. Here, this is a problem. Like you can probably draw a diagram or something. Do you want diagram? Okay, I'll not give you that. Okay, you want the diagram. Such lazy people in my class today. Weird. And like there's a deadly silence that I just can't get rid of. I mean, yeah. Sad. Here goes diagram. Bruh, you already like read the problem. You looked at the diagram and you identified the spice sim as the same one of Inmo. That's very odd. And if anybody has a solution or some ideas, just go ahead, like speak up. Because if you're going to give me a solution soon, I'll end the class soon. So yeah.
Am I
Okay.
allowed to speak?
Of course.
The
Sure.
the AM equals C in config. That's like the one from like the P3
Inmo.
of the Enmo mock in
Yes.
Sophie.
Yeah.
So there's that cyclic quadrilateral.
Yes. Yeah.
And what do you mean wrong, Adish? Who's the right Adish? Oh, the IJSO methodist. Yeah, okay.
Wait, what is that K thing? I didn't get the notation.
K thing.
Like,
K is defined. to be Mn cap AC.
What's the brackets with the dot
Oh no,
inside
that's
it?
like probably a typo, I guess.
Oh, okay.
Okay, any progress? Oh my god. What? Oh, there's also actually a Sophie class going on. I see.
So could Q
Yes.
be in center of ANC also?
Q is in
Q could
center.
be in center of ANC also. It looks like that.
AMC.
No, ANC.
ANC. Okay. Uh, let's see. I'll just GGB it. ANC, you say.
Wait, no, sorry, I don't think it is.
Let me just check. No, it is not. No. Doesn't lie on the bisector. No. Yeah, it looks like that. Yeah.
What are D and X?
D and X are something that I have defined. Ignore. Damn, I spoiled the points. No, I'm not gonna show the diagram anymore. Damn. Okay, this is a finished GGB diagram. Okay, I'll just remove D and X. You know what? This is so bad. DX. Yeah, sure. Here's the diagram. I think this is worse in a sense, but yeah.
How do we know R and CK?
Huh? R is midpoint of RKBC.
Yeah, so why is R on NCK? Okay, wait, this looks,
NCA.
it looks Bison.
It does
It
look
looks
spicy.
Miquel.
Yes.
It is Miquel. R is the Miquel.
That is the point. Okay. So I'm just gonna write it down. So R is Miquel of AMNC. Yeah.
Okay, wait, I don't know why is R the Miquel. 1 second.
Okay, Lama, but it is. Just take a minute to think about it. It is. So just take center of Spicem. Sophie mock Lama. Okay, Lama. It's fine. What Sophie marks? Okay, if it is the Miquel point of AM, like NC, what is it going to take to be similar, right? It's going to take the segment MN to AC. So it is basically going to take N to C and M to A. So it is enough to show that triangle RNM is similar to triangle RCA, which is true, right? By Sophie Moklama. Okay, no, I won't do that. I'm not as brutal. Wait. So the point is that if you have a triangle ABC, and if you have 2 points on the segments AB and like AC, D and E, such that BD is equal to CE, then the intersection, okay, I'll not draw and make a fool out of myself. ADE intersection ABC.
AD pass through the midpoint of arc BC, right?
Perfect, yes. Major arc mid in ABC. You could try to prove this. I mean it's an easy proof. You can just try to do it now. Yeah. Anybody has a proof? Okay, I'm really going over time now.
Okay, the triangle MBD is congruent to MEC.
Perfect, yeah. And that is because this is equal to this is equal to this, and third one, what is it?
Angle.
Yes, perfect. Done. So we have this lemma. Like, also Adish, like, is this Sophie Mach 3 lemma? I don't know. Is this the one?
Yeah, this was the one like the MDES cyclic was the.
Acha, okay, yeah.
Yeah.
Okay. So this is fine, I guess. Yes. So R is the major arc midpoint, and M and like just see that ABC is exactly in the config that I discussed. So like since AM and CN are equal, then you get that RMA and RNC are congruent, hence similar, right? So M to A, N to C का spiral sim center is R. So like R is the Miquel point of AMCN. Does that make sense to everybody?
Yes.
Perfect. So if R is the center of spy sim, like a lot of stuff is already reduced. So you get RNC is similar to RMA. Can you see that? Like RNC similar to actually congruent to RMA, which gives rise to this. So I'll just write it like that. Okay. Now I will like introduce my very famous X and Y points. This might seem a bit weird, but it will not.
You
Oh,
mean
wow.
D and X points?
Not D. This is Y. Sorry, GGB should, I guess. Yeah. So basically, X is the midpoint of arc AM. In circumcircle of AMK. And I'm taking circumcircle of AMK because like this is a complete quadrilateral, right? And it passes through R. And I'm also taking Y to be the midpoint of arc in circumcircle of CNK. And what is the motivation behind this? Like the first thing is obviously the Miquel thing. That is like, this is a complete quad, so both of these circles pass through R. And the second thing is that P and Q both lie on the internal angle bisector of AKM, right? So this line, like KPQ, is actually a very relevant line here. Does that make sense?
Yes.
Yes. So now I will make a claim which is like X and Y are the circumcenters of MPA and NQC. So like X is center MPA. Y is center in QC. Can you see Y?
Inside red center, right?
Perfect. Yeah. So IEL gives this. So this is nice. And like also notice that RNC and RMA triangles are congruent. Like RNC and RMA are congruent. So the point is that angle RMA is equal to angle RNC. So like due to this okay. Never mind. Okay. So RNC and RMA are congruent. We had that previously. So doesn't this mean that radius of circle RNC equal to radius of circle RMA? Can you check? So
Yes.
these circles are like have equal radius, right? Make sense?
Yes.
Yeah, perfect. So like that is going to mean Rx is equal to Ry, right? Like obviously Rx is equal to Ry because the same spicem is going to send it there, right?
Yes.
So Rx equal to Ry, and like R is still the center of spicem that sends xy to AC and stuff. So and also you have Qy equal to xp, right? So that is just going to finish key Rp is equal to Rq. Does that make sense? Like Rx is equal to Ry, and you already had that Qy is equal to xp because circumcenter. So Rp is going to be equal to Rq in the sense that like all of these like xy and pq share the common perpendicular bisector. Just this line. Does that make sense?
Yes.
Okay, great then. Like okay, I just got one yes. Like did it make sense to everybody else?
Yes.
Okay, great then. Okay, why is everybody flooding me with a nice solution? Thanks, I guess.
Could you
What?
just repeat that last part? Like,
Okay, sure. So the point is that x and y are the circumcenters of these three, like these two, APM and NQC, right?
yeah,
This makes sense?
yes, yeah,
And Rx is also equal to Ry, right?
yes,
And Qx is equal to Qy because these are the circumradii of these two circles, small circles.
yeah,
And these circles are congruent because this being the like these I just said that like the big two circles have the same radius, so these two also have the same radius, right?
yeah,
So like you kind of have a configuration where you have two sides of equal length and you have like one thing and you have 2 points here that have equal lengths. So these two triangles, this one and this one, are congruent, right?
yeah.
So
Uh,
this and this have equal length, which is what we
thank
said.
you.
Yeah, no problem. Okay, I think I'll end here. Sorry for going 15 minutes over time. Okay, have fun then. Bye. I hope you liked the class. Like, any questions, feel free to DM me anytime. And don't worry about bothering me. So, yeah. Bye bye.
Thanks. Bye.